Hello and welcome back, everyone. Once again, this is MIET 312, and today we're going to be talking about surface mine equipment selection and sizing. We're going to get started right into this, and like the blasting section, this is going to be a bunch of equations again. So buckle up and get ready for this, and here we go. So after we blasted all the rock, somebody's probably going to ask, we got to move it, right? And to do that, we're going to need to determine the bucket size. And bucket capacity is once again a bunch of variables, and they're listed on the next screen. And so here we have a huge list where BC is the bucket capacity. In bank volume, so bank cubic yards, that means in place cubic yards. Once you blast it, then it will take up more volume, and that includes what we call swell factor. So we're calculating it in bank yards. So when you would do like an overburden calculation and you calculate that volume, either using software like Carlson software or something like that, or you're using in analytical techniques, just math to solve it. Either way, we're calculating this in bank volume. Q is the production required, so we're talking about cubic yards per hour. If you want to equate that to tons per hour, you'll have to take in the stripping ratio and that sort of thing. So how much you have to remove per ton of coal, and then you can do it that way if you need to. C, theoretical cycles per hour. For a 90-degree swing, it's 60 divided by the time in minutes that would take to make a 90-degree swing. Values of C can also be obtained from manufacturer's literature or your own time studies. A lot of these things will be your own time studies and that sort of thing. Mechanical availability during scheduled hours of work. So what percentage of the time is your equipment operable and not broken down? Job operational factor. We're sizing this shovel in this case. It's part of a system, and so there can be delays due to a number of things. It can be management. There can be labor issues. Mine conditions, the job conditions, right? That all factors into the operational factor. The bucket fill factor can be described as the fillability divided by the swell factor. Fillability is the loose volume of material excavated in an average load, so how much you load up in an average bucket as a ratio of the capacity. So how full can you get the bucket is what it's trying to say. And so you can determine that from field measurements, but there's also going to be tables here in this presentation that can give you an approximate idea. Then swell factor is defined as the unit volume, the bank unit volume, the weight of that per unit volume. So pounds per cubic foot, tons per cubic foot, and then the weight per unit volume loose, right? So you have the bank volume divided, or the weight per unit bank volume divided by the weight per unit loose volume. And that gives you the swell factor, sometimes called the balking factor. And then the reciprocal of the swell factor is the percent swell. So it would give you what percentage it increases. Swing factor, so we usually are determining this based on a 90-degree swing for a shovel at least. It could be less, it could be more, but you don't want to get too far off that. Otherwise, you're trying to load in a less than ideal situation. And then the propel time factor. So this factor takes into account the time it takes a shovel to maneuver, right, from place to place. You know that from time studies. I performed them myself actually on a 53-yard Sears electric shovel. I spent a whole week with that piece of equipment and the trucks associated with it. So you can come up with a lot of these times for that, and for all these things. So here's table 10.3. This is the shovel operating efficiency. And you can range anywhere from 54 to 83%, basically. Given excellent job or mine site conditions, and then also excellent management. So we've sized everything appropriately. We have the right number of trucks, that sort of thing. All is well. Roads are good. That's job conditions. Could be a little bit of management too, if you think about it. So there's a pretty big range here, and it just gives you an idea of where you might be. And then we have another huge table of parameters here. You might have to zoom in here, and we have the bank density, swell factor, and the fillability. Those other things we discussed for various materials. This includes everything from asbestos ore to sandstone and shale, right? Different clays and gravels, coal, there's limestone in here, iron ore, pretty much a lot of the things you'd be expected to find at a surface mine. You can find them in this table. So more tables for shovels. The swing factor, so you have different angles. So if it's 45, you're going to load faster, right? So it's bigger than 1. If it's 135, 150, it's less than 1. I don't think we would ever be loading behind the shovel. I'm not going to say it's impossible to load behind the shovel, but you can also do 180, and it's even less than that. So that's the swing factor. Propel time factor, it varies on the type of mine, and in this case runs from 75% to 95%, right? 0.75 to 0.95, and differs based on the conditions that would be expected at those types of mines. So what about drag line? There's still drag lines out there in operation. There's no very large ones in West Virginia anymore. I'm sure if you look hard enough, there's probably a small one out there somewhere. But anywho, they do exist. They are very large, and the critical sort of parameter for sizing a drag line is how far can it reach, right? And we're going to be calculating these two distances here, the R sub D and R sub DD. And in this case, okay, R sub D is the reach of the drag line from the edge of the bench here. So it's right on the top, and that's the reach. And then we're also going to calculate it back to the center point, and that's two separate equations. Well, the first one is R sub D, the reach of the drag line in feet. S sub P is the swell. E sub T is the outside diameter of the drag line tub. Let's go back at that 1 second. You see E sub T labeled here, so it's what the drag line is basically sitting on. And that's its rotation point, center of rotation. So that is the center of the tub. So let's assume the drag line is offset from the high wall for a distance 3/4 of the tub diameter. In this case, back again, we've got that 0.75 E sub T that goes from the edge of the high wall back to the center of the tub. And so after that, you can calculate the R sub D as R sub D plus 0.75 times E sub T, right? So it's just this, the top equation, plus that little bit of distance back to the center of the tub. And that's considered the dumping radius. But what if it's working on a bench like this one? So our previous, our photo, 10.7, we've got a drag line. It's sitting on top of the pit here. And then there's a bench, in this case, we've got this extra material, and most of this calculation is going to be the same, except it adds in an additional factor for this for working on the bench, right? All the other parameters are the same. We still have our swell in here, the various heights, and this gives you the R sub D for that. And then you could get the R sub DD, the swing radius, by adding on 0.75 times the tub once again. And I almost decided to skip stripping shovels because they're just not used anymore, at least not to any degree of high levels of production. The last that I'm aware of that these ran in the United States was the Silver Spade and another large stripping shovel that Consol used in Ohio, surface mines in Ohio. And so in this case, you're not actually loading a truck with the shovel, right? It's simply picking up the overburden and then moving it to the side. So once again, we have this sort of same calculation, right, for the shovel. And here we calculate the R sub S, so the shovel's reach, and that's calculated using some angles again, the swell factor, and T as well. And then the dumping radius, so if this F sub C is equal to the width across both crawlers in feet, so this is giving us like a distance there towards the center of the piece of equipment, we take the original R sub S and then add half of the F sub C, so the width across the crawlers. We get half of that, and that gives us that little bit of extra distance for the dumping radius. Bulldozers, on the other hand, are used a lot. Extremely useful for dozing material for short distances, so pushing material is what they're doing. And the selection of a suitable bulldozer can be accomplished by determining the blade size in cubic yards, and the choice of blade depends on the applications and soil conditions. So you'll use the following 7 equations to come up with this blade design. So we have FT, which is the fixed time in minutes. So we have travel time, TF, and loaded. Okay, that's a loaded time in minutes, and then of course empty, tramming and reverse to go remove more material, is VT. No, it's TE. Sorry, TF is the travel time, loaded in minutes. TE is the travel time empty. VT is the variable time in minutes. MT is the maneuvering time in minutes. So just like we have the shovel maneuvering time, we have maneuvering time for the dozers as well. And CT is the cycle time. LT is the loading time in minutes, and MPH is the number of passes per hour, whereas PPH is the theoretical production per hour in cubic yards. So we have all these numbers sort of going in, and it's all related to one, the amount of production that you intend, and all the travel time and the cycle time and all those times put together. So all the time you're moving the equipment, right? And then max pH is the actual production per hour in cubic yards. HD is the haul distance in feet. S1 is the loaded speed in miles an hour. S2 is the empty speed in miles an hour. B sub B is the blade size in cubic yards. L sub F is the load factor. B sub F, or BF is the blade factor, and AO is the operating factor. So there are many possible applicable correction factors that go into this. A lot of those can come out of handbooks. and other things like the material grade, visibility, transmission, all that stuff can be found from manufacturers or other sources. Okay, so these don't necessarily have all the charts necessary to calculate these numbers because most of it is going to be dependent upon site-specific conditions, right? And I say this is a civil engineering class. Why are we talking about scrapers? But occasionally, they are used in mining and any situation where you need to remove topsoil. So equations 31 and 32 here, very similar, to the bulldozer calculation. It's basically the same thing. It's based on the number of cycles, how far you're hauling it, right? So how far you're going, the number of cycles per hour, and then how much you need to transport in cubic yards. How much production do you need? And another reason I put this in here is they do have a question on the West Virginia 40-hour surface miner exam about scrapers or pans in this case, and it's a safety related question, but it is still in there as far as I know, unless they changed it since when I took it. So, and they also have calculations for the number of pusher tractors. So you can calculate the number of scrapers per pusher based on the scraper cycle time and the pusher cycle time. Pushers tend to be used to load the scraper or pans. So what they'll do is sometimes they'll get a lot of times they'll get hung up trying to fill their bucket full of dirt, and so while they're loading, you'll get a pusher to push it along, right? And it scrapes up soil as it gets pushed forward. So you're only using those during loading, and so your pusher cycle time is going to be much less than the scraper cycle time. So you can get the number of pusher tractors that you need by taking the total number of scrapers and then dividing by the number of scrapers per pusher. It's going to be more than one, unless you only have one. Here's some charts from Caterpillar in 1997. These most likely have been updated since then, but it gives you loaded distance versus time, unloaded distance versus time. That's in there again for some reason. And then finally, after all of that, we have the front end loader selection. And there are SAE ratings for front end loader bucket capacities. There's the strut capacity, the volume contained in a bucket after a load is leveled by drawing a straight edge. B, the heaped or rated capacity. So this is like you just pick up a bucket full. It's the strike capacity plus whatever is heaped on there. That's the rated capacity for the front end loader. And then you have the static tipping load. So the minimum weight at the center of gravity for the bucket, which will rotate near the machine, which will rotate the rear of the machine. So how much can you put in the bucket before it basically picks the back wheels up off the ground? And as in both the bulldozer and the scraper calculations, bucket capacity in cubic yards is based on the hourly production, right? So how much you're going to produce in cubic yards per hour. MPH is equal to 60 divided by CT, which is the cycle time in minutes. So dumping time plus maneuvering time plus loading time. So you have the cycle time, which is lots of times put together, load factor, the bucket factor, and the operating factor again. So once again, these are all theoretical productions based on, or theoretical bucket sizes, capacities, based on the amount of production that you need, and then divided by everything else. And so with that, we're going to conclude this presentation on surface mine equipment selection. I've specifically left out an important part of this, and that is going to be the truck shovel or truck loader calculations. We're going to do those separately, and we're going to go into a lot more detail on those because those are probably the most important for us, geographically speaking, in this region. It's the most important thing you're going to need to know, right, about equipment, and that is how to, make sure that your trucks are not over or undersized, based on the size of what you're loading it with. And like I said, we'll get into that in a lot more detail next time. And until then, we'll see you.